Okay, so this question is all about nuclear decay, okay, and the operation of a power station. So information about two natural isotopes of uranium is given in the table. So we've got here uranium-235, which undergoes alpha decay. It has a half-life of 7 times 10 to the 8 years, okay, and it produces another isotope called thorium-231. Uranium-238 also undergoes alpha decay. It has a half-life of 4.5 times 10 to the 9 years, okay, which is a long time, and it produces thorium-234. One type of fission reaction involving thorium-235 is shown in the diagram. Okay, so we've got here our typical chain reaction. We've got a neutron coming into this uranium atom. That then becomes unstable and it breaks down into krypton and barium. Okay, also we produce some more neutrons. Okay, and those neutrons go out on and they produce another nuclear fission. Okay, which then goes on to produce further nuclear fission. So every step produces 3 new steps. Okay, and if that happens uncontrollably, that's when we have either a nuclear meltdown or, worse still, a nuclear explosion. So another type of reaction occurs in a fast breeder fission nuclear reactor. Uranium-238 can be used to generate plutonium-239, which also acts as a reactor fuel supply. An intermediate stage involves the production of neptunium-239. The reaction follows the 3 stages below. So we can see that uranium-238, if you add a neutron to it, it becomes uranium-239. Uranium-239 becomes neptunium-239 plus a beta particle, and then neptunium-239 becomes plutonium-239 plus another beta particle. Okay, so this page here is all for information, and it may or may not be asked on in the next part of the question. Okay, so first question says, state what is meant by the term half-life. Okay, so half-life is a time, it's a time period, so time taken for a halving, in other words, when we're about to talk about halves of, so we could say radioactivity, or the mass of an isotope. Okay, so the isotopes decay into something else, so that takes the half time, or the amount of material. Now, personally, I would probably suggest you use a halving of the radioactivity, okay, but any of these three will get you a mark, okay, because they all come from the same process. So, excuse me, the isotopes of uranium in the table have been in existence since the Earth was formed. One estimate of the Earth's age is 4.2 billion years. Calculate the fraction of uranium-235 that remains on Earth today. Okay, so perhaps the easiest way to look at this question is to turn 4.2 billion into standard form, because that's the format in which the numbers on the other side have been written. So standard form for 4.2 billion years would be 4.2 times 10 to the power 9, okay, because billion is to the power 9, all right? And then in order to work this answer out, we need to know how many half-lives that is for uranium-235. So if we have a look, uranium-235 has a half-life of 7 times 10 to the 8. Okay, so if we divide that value there by 7 times 10 to the power 8, I would strongly advise that you have a calculator available to you in your exam. Okay, so if we do 4.2 to the power 9, or times 10 to the power 9, and divide that by 7 times 10 to the power 8, then we get 6. Okay, so that's 6 half-lives. But the question asks us the fraction of uranium-235 that remain on Earth today. Okay, so in order to calculate that, we need to use this figure here in another equation. So the fraction left is 1 over 2 to the power n, where n is this value here. Okay, so that's 1 divided by 2 to the power 6. Okay, so if we cancel this and we put in 2, and we've got, where's it gone there, to the power 6 is 64. Okay, so 2 to the power 6 is 64. So that's 2 times 2 times 2 times 2, 6 times. Okay, so that equals a 64th. So a 64th of the original uranium-235 is left on Earth today. So we'll put that there. Okay. If you're not sure about this method, what you can do is you can start off with 1. That's the whole amount of uranium-235. And if you do go through this process 6 times, so that's 1 half-life, 2 half-lives, so we've halved that, 3 half-lives, 4 half-lives, 5 half-lives, and then finally our 6th half-life gives us 1 over 64. So each of these steps is a half-life, and during each of those steps the amount of material or the amount of radiation goes to half its original value. So 1 to a half, then to a quarter, then to an eighth, and so on. Okay, so you get the same answer, slightly longer process, but perhaps more reliable, maybe. Okay, this question here, explain how the uncontrolled chain reaction shown in the diagram is prevented in a nuclear reactor. So if we have a look at the diagram, the key thing we need to be aware of are these neutrons. Okay, so every time neutrons are made, that's where we can actually prevent the reaction getting any worse, because these neutrons are a special speed of neutron. They're slow neutrons, and so the boron, okay, can actually absorb the control rods rather. So the control rods in the reactor can be lowered to absorb the neutrons and prevent further fission, and therefore more neutrons being produced. Okay, so every time the uranium atom splits, it gives off 3 or possibly more neutrons, and those go on possibly to cause further fission reactions. So if you can stop that by lowering the control rods, then you can prevent the reactor getting into a runaway situation or into an uncontrolled chain reaction. Okay. The next question says, describe the structure of the nucleus of 14156 barium, which is one of the fission products. What it wants to know is what's in the nucleus of barium. So to answer this question, you have to remember what these numbers tell us about the nucleus of barium. Okay, so we can say that barium has 56 protons. Okay, so we know that because the proton number or the atomic number is the number of protons. And to show the examiner you understand where it's coming from, you could write 141 take away 56. Okay, so to make sure we get that absolutely right, again, the possession of a calculator in your exam is a very, very good idea. Okay, so 141 take away 56 is 85. So 85 neutrons. Okay, so the question's got 2 marks, and there are 2 key facts there, so that should get you the mark. Okay, but if you put this bit in, it shows the examiner where it's from, just if there's any doubt if you make an error with your subtraction. Okay. And then the final part of this question says complete the following nuclear equations showing how uranium-238 generates plutonium. So in order to answer these questions, we need to remember that we're looking either side of the arrow to ensure that the atomic masses are the same on the left as they are on the right. So just for the sake of checking, 238 plus 1 is 239. So obviously the examiner's got that bit right. And the same is true underneath the the atomic numbers also have to be the same either side of the arrow. So 92 plus 0 gives us 92, which makes sense because we've gone from uranium to another form of uranium. Okay, so the atomic number, the number of neutrons should stay the same. Okay, now this question will involve a little bit of knowledge, but also the same process as previously. Excuse me. But to answer this question, and indeed this question, you have to know that a beta particle is a free electron, and because it's a free electron, it has got no mass. However, because it's an electron, we consider its atomic number to be -1. So these are both -1. Okay, so once you've got that information, you can then do the same process as you did previously, although the atomic number of uranium is missing from this one, but as it's in the previous question twice, then we can assume that that's not going to change. So that's a 92. Okay, so once we've got that 92 there, we need to make sure that on this side of the arrow, there's also an atomic number of 92. Okay, now the only information we've got is that that's a -1, so you need to ask yourself, what number do I write here? That when added these two numbers together, you get 92. And that would be 93, okay, because 93 add -1 is 92. Okay, so that's a 93. Now, having established that that's 93 there, okay, and this is the next stage, we can assume that that's a 93. Okay, and if we look across the top, we know that the mass on this side is 239, and currently the mass here is 0, so that must be 239, okay, because you've got to maintain the same mass on either side of the arrow, and you've also got to maintain the same atomic number on either side of the arrow. Now this is a 93 and this is a -1, so this here must be 94, okay, because 94 take away 1 is 93. Okay, that's that question there.